In this video, we're going to look at a hypothesis test for the difference of population proportions. And this is going to be very similar to the previous section where we did a hypothesis test for the difference of means. The only difference is we're going to be looking at population proportions instead. So if we think back to chapter 9, when we were doing hypothesis tests for a single mean or hypothesis test for a single population proportion, it's going to be the same type of distinction between the two. So they're going to be very similar with just a few little updates. So let me go through what some of those updates are now. The first thing we're going to need to be aware of is that there's a little bit of new notation. Just like in section 11.1, the section right before this, when we were doing a hypothesis test for the difference of means, we had 2 of everything. And we're going to have 2 of everything here as well. So there's going to be P1 and P2, and these are the 2 population proportions that we're interested in studying. So these are the population proportions of interest. We will also have x1 and x2. These are going to be the number of individuals in our 2 samples. So these are the number of individuals in our 2 samples, because we're looking at 2 different groups here again. That fall into whatever category we're interested in studying. So in the category of interest. We're also going to have N1 and N2, which are going to be the 2 sample sizes. And these will give us P1 hat and P2 hat, which are respectively, this one over here is going to be equal to x1 over n1, this one's going to be x2 over n2. These are the sample proportions of interest. So these are the samples that we're using to study. We're using these 2 values to study and hopefully be good estimates of these 2 values. That's kind of the idea. So we also have a list of conditions that need to be met in order for us to perform one of these. And these should look familiar. We've seen these in the previous sections. So the first one is that we need a simple random sample, and in this case, because we're taking 2 samples, they also need to be independent. So we need simple, random, and independent samples. And again, the independence just means that the outcomes of one of our samples shouldn't affect the outcome in the other sample. The second one is that we need each of the so basically each of the 2 populations that we're studying need to be 20 times larger than our sample. So our 2 samples each need to be less than 5% of the total populations. So each population must be, let's write it this way. Each population at least 20 times larger than each sample. We can only have 2 categories, and again, this is because when we're dealing with these population proportion problems, they're kind of related to binomial distribution, and so get the correct number in there. Only 2 categories. There we go. So it's related to a binomial distribution where we have to basically split everything into success or failure, and there are only two possible categories. And the last one is that both samples must contain at least 10 individuals in each of the two categories. So both samples contain at least 10 individuals in each category. And if these conditions are met, then we can proceed. And the procedure for this thing should also look familiar. It's the same 6-step procedure that we've now done, I don't know, 4 other times, 5 other times, I don't know. So the step 1 is always state the null and alternate hypothesis. And in this case, the form of the null and alternate hypothesis are as follows. The null hypothesis, we're going to assume that the two population proportions are the same. So another way to phrase that is we could phrase it as P1 minus P2 equals 0, that there's no difference between the two population proportions. And the alternate hypothesis will take one of the many forms we've talked about, with either P1 greater than P2, P1 less than P2, or P1 simply not equal to P2. And we can rewrite each of these in the same way that we did right here by subtracting P2 from both sides. So this one could be rewritten as P1 minus P2 is greater than 0. This one would be P1 minus P2 less than 0. And this one would be P1 minus P2 not equal to 0. And that makes it clear that we've got our right, left, and two-tailed versions. Hopefully more clear at least. Because in this case, the number that we find this difference is greater than 0. Greater on our number line is further to the right. In this one, P1 minus 2 is less than 0. Less than on our number line is further to the left. And this one is the two-tailed case where it could be either direction, greater than or less than. The second step is where we are going to define what we consider weird. And again, depending on the approach that we take, we're going to do this the exact same way that we've been doing this. So if we're doing the p-value method, we just need to give the significance level, which is alpha. And if we're doing the critical value method, we need to actually find the critical value. And all we need to remember is that in the case where we're dealing with a population proportion, our critical value is going to be a z-score, not a t-score. So we need to find the critical value, which is either, in this case, z sub alpha, negative z sub alpha, or plus or minus z sub alpha over 2. There's all of our different cases for the given value of alpha. But again, it's a z-score when we're dealing with population proportions. So the only time we'll ever use a t-score, again, is when we're dealing with S. If S shows up in the problem, that's when we use a t-score. S and t go together. Third step, we need to compute the test statistic. And this is really the only significantly different piece. This formula looks different than the others, so let's compute the test statistic. And in this case, the test statistic is the following. So it's a z-score, and it looks like the following. We look at the difference between the two p-hat values. We subtract off the presumed difference of the actual population proportions, not from our sample. And then we divide by the standard error, which in this case looks like the following. So it looks like p-hat times 1 minus p-hat times 1 over n1 plus 1 over n2. So this formula is just getting uglier and uglier and uglier. And in fact, as I point out a few things in here, this right here, P1 minus P2, that is always the assumption that we get from the null hypothesis. So this piece comes from the null hypothesis. And in this case, the presumption is, according to our null hypothesis, that P1 minus P2, which is what we've got right here, is equal to 0. So again, most of the time we'll just cross that term off. That's a 0. This is our evidence. And this term over here is our standard error. But notice in our standard error, it involves this p-hat term. We don't have a p-hat in this problem. We have two different p-hats. We have p-hat 1 and p-hat 2, but we don't have p-hat. And so I need to define what this is. This is sort of the combined p-hat. So let me just make it totally clear where this p-hat thing that we're writing right there is called the pooled proportion. And it comes by taking x1 plus x2 and dividing that by n1 plus n2. And so this thing right here is what goes in right there and right there, and it's called the pooled proportion. So this formula is a pain in the butt if you're actually plugging these numbers in directly. Down the line, I'll show you how to do this on the calculator, and this is one of the things that the calculator spits out for us. It will give us the test statistics, so we don't necessarily have to try to plug all of those numbers in by hand. Step 4 is basically, again, same as before. If we're doing the critical value method, we get to skip this step because we've already got the two z-scores that we're going to compare. We have the critical value and we have our test statistics, so we have everything we need for our comparison. And if we're doing the p-value method, this is where we actually find the p-value, which is the area to the extreme of the test statistic. And we find this so that we have the two areas that we're going to compare. The p-value is an area, and we would compare it to the significance level alpha if we're doing the p-value approach. So that is the idea. Step number 5 is where we determine if our result is weird. And at this point, these are identical to the things that we've been writing in the previous sections. In fact, in the next video, maybe I'll even leave these off entirely. Just say ditto. This is exactly the same as what we just did before. So we're going to determine if our result is weird. What determines if it's weird? In the case of the p-value method, it's weird if the p-value is less than alpha, which is our significance level. There we go. And if we're doing the critical value method, our result is weird if the test statistic, which is z, is more extreme, so further into the tail than the critical value, which was our cutoff for where we consider weird. And that can be either z sub alpha, negative z sub alpha, or plus or minus z sub alpha over 2, depending on whether we are right-tailed, left-tailed, or two-tailed. And if our result is weird, then we reject the null hypothesis. So reject the null hypothesis if our result is weird. And step number 6 is where we state our conclusion in plain English. Okay, so there are our 6 steps of our procedure. They are the same 6 steps, and really the only major differences come in step 1. We have kind of a different format for the null and alternate hypothesis that involve 2 different values, p1 and p2. And then step 3, the test statistic, is a bigger, uglier formula than the ones that we've seen so far. So let's do an example. We'll do it doing all the steps, and then we will also do it on the calculator. So let me zoom in here and we can do an example. Okay, so here's our example. We want to answer the question, are college students more likely to use, in fact, you know what, I'm going to switch this up. We have not done a two-tailed hypothesis yet, so let me do one where we can do a two-tailed hypothesis here. Let's try this. Okay, let me rephrase this. Do college students and high school students use Instagram at different rates? Meaning, what proportion, does the proportion of college students that use Instagram differ from the proportion of high school students that use Instagram? Well, let's say a simple random sample of 360 high school students showed that, let's see, 167 use Instagram, while 213 out of 430 college students used it. And I want us to use, I don't know, let's use a significance level that's different than some of the ones that we've done before. Let's use a significance level of, I don't know, alpha equals 0.1. Okay, so here's our question. Do college students and high school students use Instagram at different rates? We see that 167 out of 360 high school students use it, while 213 out of 430 college students use it. So we want to see if those two proportions are different enough that we suspect that it's strong enough evidence to suspect that college and high school students actually use Instagram at different rates. So, going up to our conditions, can I fit them all on the same page? Hopefully that's readable. We'll find out. We have our two simple random independent samples, right? We sampled the high school students and the college students. We sampled them separately. One group does not impact the other. Each population is at least 20 times larger than each sample, so our samples were 430 and 360, and the total number of high school students is definitely at least 20 times more than this number, 360, and same with college students. It's certainly at least 20 times larger than this number, 430. We've only got two categories. Basically, in our sample, we're asking them, do you use Instagram or not? So the two categories are yes and no answers to that, essentially. It's a yes or no type question. And lastly, do both samples contain at least 10 individuals in each category? Well, the first one was 167 did use Instagram out of the 360. That leaves almost 200 people that didn't. And similarly for high school, 213, that's definitely more than 10, and the remaining number, which looks like it'd be, what, another 210-ish, 215-ish, did not. Both of those numbers are bigger than 10. So we've met all four of our conditions up here. We can proceed with our procedure. Let me zoom back in here. There we go. Okay. I'm not sure which method we used last time. Most of these examples we've been doing both methods. I can't remember. Maybe we did the p-value last time. Maybe we did the critical value method last time. In this case, I'm just going to do both, again, just for practice. But again, you are not required to do both procedures. So, step one. Doesn't matter which procedure we take. We need to state the null and alternate hypothesis. And so our null hypothesis and our alternate hypothesis. The null hypothesis we already saw is that P1 equals P2, that the answer to the question up here is no. They don't use it at different rates. The proportion of high school students and college students that use Instagram are the same. So we could rewrite that as P1 minus P2 equals 0 if we want to think about it like that. And the alternate hypothesis, based on the phrasing of the question here, it doesn't ask are college students more likely or are high school students more likely. It just says, does it differ at all? So the key word is this different. The word different, the fact that we're just interested in whether the rates are different, not whether one is bigger than the other, tells us that this is a two-tailed hypothesis, that we're interested, our alternate hypothesis is that P1 is not equal to P2. Alternatively, we could write that as P1 minus P2 not equal to 0. So this makes this two-tailed, which again is kind of by design. I don't think we've done an example of a two-tailed hypothesis yet. We do need to keep track of which group we're calling which. So I'm going to do a little table just like we did on the previous one here. We'll list off the values we're interested in keeping track of. So I'm interested in keeping track of basically the x values, the n values, the p hat values to ultimately answer a question about the values of p, which are the population proportions. And we've got group 1 and group 2. And we get to pick which one you want to call high school students, which one we want to call college students. So I'm going to say in this case, I'm going to call this group college and this group high school. But you could totally pick it the other way around. It wouldn't actually affect the end result of this. So let me just fill these all in, and we can figure out the values that we're going to use for each one. Okay. So P1 and P2, these are the things that I'm never going to actually know. These are what we're trying to draw conclusions about, these values down at the bottom. These are the values, sorry, right here. These are the values that we do know that are given in the problem. So for college students, what number out of what number used Instagram? Well, it said it was 213. That's going to be my value of x out of my total sample size, which was 430. That's the proportion that use Instagram. And over here for the high school students, it was 167 out of 360. And these two numbers I get by taking the proportion x over n. So I need to compute those numbers real quickly here. And when I do 213 out of 430, I get about 0.495 if I round it to 3 decimals. And when I do the high school students, let's see, 167 divided by 360, I get about 0.464. So 0.464. So this number again came from those two numbers. This came from those two numbers. I just take the ratio. 167 over 360 gave me this decimal. 213 over 430 gave me this decimal. That's based on our definition. So I've got my little table filled out. That'll help going forward. So looking at our picture, we need to define what we're going to consider weird. So in this case, if we're doing the p-value method, I consider weird to be anything that happens less than 10% of the time based on the fact that this is how we defined our alpha value right up there. So I just need to copy that value down. We're going to consider something weird if it happens less than 10% of the time in this case. And for the critical value method, I need to find the critical value associated with this thing. And because it's a two-tailed hypothesis, this is going to be z sub alpha over 2, plus or minus. There's going to be two different values. So I'm going to find this value in just a minute, and we'll figure out then and draw a picture to kind of start to illustrate what's going on here. So to find this value, I need to take a look at table A3. So let me see if I can add it on here real quickly. It is right here. Get the right table. I just want this table. Okay. So here is the table that we are going to use to find this value. Remember, our value of alpha was 0.1. So it's this number. But we have a two-tailed hypothesis. So this area of 0.1 is split evenly between the two tails. So let me draw the picture to make this a little bit more clear. Let me first, actually here, let me zoom out and move this table a little bit. Let's move it over here to the edge. We'll come look at it in a minute. But here's our picture that we've got. Let me draw it over here. So here's our picture. So this is the distribution of all the possible differences between P1 and P2 hat. All the possible differences. We are assuming, according to the null hypothesis, that the difference is 0. That is our null hypothesis. But in fact, we are going to find a difference. Clearly, our P1 hat and our P2 hat are different values. And so we'll figure out where this winds up on this curve in a minute. But for now, we've defined weird to be anything that happens less than 10% of the time. But because it's two-tailed, that means I'm taking my alpha, which is 0.1, and I'm splitting it 50-50 between the two tails. So that means there's a cutoff on this side and a cutoff on this side, and both of those areas individually are 0.05. So basically, we took, let me give myself a little more room there, 0.05 on this side, 0.05 on this side. Right. Each of these are 5% of the area for a grand total of 10% when you add them up together. So this is what it looks like in the two-tailed case. We have two separate tails. Everything over here is weird. Everything over here is weird. And all the stuff in the middle, this is where stuff is not weird. So this is the idea. We have defined the weird regions based on this picture. So comparing this picture to this picture, it looks a little bit different. I'm trying to find the z-score, and there's two of them. Here is the positive z sub alpha over 2 version on the right, and on this side it'll be the mirror image. It'll be negative z sub alpha over 2. And I want to figure out what number goes there. So what is the z-score that bounds, in this case, the top 5% of the area? How did I get that 5%? I took alpha and I divided it by 2. That's what this notation down here tells me I'm supposed to be doing. I'm supposed to take alpha, which is 0.1, and divide it by 2, and that's what gives me the 0.05. So the area I need to look up isn't alpha. I'm not looking up 0.1. I'm not going to use this number. I need to use this number because this is alpha divided by 2. So using this number, tracking it down to the bottom. So this is alpha, but I'm not using alpha. I'm using alpha over 2. So this is the number I need. And if I go down to the row labeled Z, that's the number I need. Right there. 1.645. So this number is 1.645, and this one is negative 1.645. There are my two different critical values, one at the left side, one at the right side. Those are my cutoffs, my z-scores that cut off the regions that we're considering weird. So that's what we get here, plus or minus 1.645. That is my critical value for this problem. Okay. So hopefully that makes sense over here in the picture. Again, if it was one-tailed, either left-tailed or right-tailed, I would be using this row, alpha. I would have all the area in one tail, so I'd be using 0.1. But because it was alpha over 2, because it was two-tailed, I do actually divide that number into 2 and use this row, or sorry, this column instead, and that gave me this number. So let me delete this whole table over here. And we'll come back to the problem over here. So let me zoom back in a little bit. So we've defined weird, and there's our picture. And now we need to compute the test statistic. And so this test statistic is a big, ugly formula. Remember, I'm just going to copy it down again real quickly. It's P1 hat minus P2 hat minus the difference between P1 and P2, which we already know this difference, according to the null hypothesis, is 0. So I'm not even going to bother to include that in the next part of the formula. And then I'm dividing by P hat times 1 minus P hat times 1 over N1 plus 1 over N2, where P hat is the combined pooled proportion that is x1 plus x2 over n1 plus n2. And so I'm just going to plug all of our values in. I'm just getting all of these values basically from the table up here. So just keep this in mind. Hopefully you have it written down. This is where I'm going to plug all these numbers in down here. So first things first, let's compute this p hat. Our p hat value is going to be, let's see, x1 is 213, x2 is 167. So 213 plus 167, and the two values of n were 430 and 360. And if I add those together and compute that pooled proportion, let's see, I get 380 on top, 790 on the bottom. Plug that into the calculator, and I get 0.481, it looks like. So there's the number for this pooled proportion. This number is going to get plugged in those two locations, there and there. And the other part, these two numbers, we already found them. They were in our table as well. They are these two numbers, so 0.495 and 0.464. So I'm going to have 0.495 minus 0.464 on top. Again, I'm going to ignore this minus 0. We don't really need that. Let's toss parentheses around this real quickly to make it a little cleaner. And in the bottom, I'll use that 0.481 that we just found over here. So 0.481 times 1 minus 0.481. And then I'm multiplying that by 1 over 430 plus 1 over 360. And now I'm just going to plug these all into the calculator and see what we get. So just give me a minute here. And I get about 0.869-ish, or if we're just going to use two decimals, about 0.87. I guess I can just use 0.87. Good enough. Okay, so there's my test statistic, 0.87. So that z-score clearly is going to wind up being 0.87. That's going to be, I don't know, here-ish. Here's that test statistic, z equals 0.87. Right off the bat, we can tell now, based on this picture, is this a weird result? No, clearly it falls into the not weird region. So we already know we're not getting a weird result if I'm doing the critical value method, because I'm comparing this number here to this number here. If we're going to do the p-value method, I need to find the area associated with this. So I'm wanting to find now this area. that big area from there all the way over to there, that's going to be the p-value. That's the next step. So step 4, let's find that p-value. So again, if we're doing the critical value method in step 4, we get to skip it. I've already compared the two values, the two z-scores, so we're skipping it. I've got everything I need. But if we're doing the p-value method, I need the p-value. So what is the p-value? It's going to be p-value is the area to the extreme of our test statistic. And so I want to make something totally clear. Let me go back up to this picture here. Oops. I have two choices when we do this problem, and so let me explain. This is actually not quite the p-value. I've found the area associated with the right side, and it would only make sense if I compared this shaded region to this region that's in the one tail. It wouldn't make sense for me to compare this big region that I've just now shaded to this original value of alpha. So I can either just compare the values in one tail, which would mean this full shaded region, to just this 0.05 to alpha over 2, or I can find what, and this is the way that the book does it, they'll actually find the combined, the combined area of both that shaded region and its mirror image, and this combined area, let me see if I can find a way to sneak this in here, that combined area as well gets mixed into the p-value. So both tails get mixed together, and then it's fair to compare this combined both shaded regions to the combined original area alpha that was split between both tails. So hopefully it makes sense. I can either compare just the numbers in one tail, 0.05 to whatever this area happens to be, or if I want to compare to the original alpha rather than alpha over 2, right? This number right here is alpha over 2. Instead of comparing to alpha over 2, if I want to compare to alpha, I need to find this area, and then I need to double it to take its mirror image into account as well. And that is the way that the book is going to do it. So when I say the area to the extreme of the test statistic, I really mean that combined shaded area that shows up on both sides. So if we get back out our tables, let me add a table in. Remember, we're using a normal distribution, a z-score, so we're allowed to use table A2. And I want the area to the right of this 0.87. And then I'm going to have to double that area so that I also get the one to the left of negative 0.87. So let's open up these tables again. And let's see. Let me just do this one. I can get away with just doing this one. So here is part of table A2. Again, I'm using this one to show. Let's move it over to the side. I think we can still see it on our screen. Good enough. I picked the negative one, so I'm really just looking for this area over here on the left. It's the area to the left of z equals the mirror image of this, so z equals negative 0.87. So that's the number I want to use over here. I want to use negative 0.87. So here's negative 0.8, 0.07. What number is sitting there? Boom, boom. There's the number, 0.1922. So in this case, area to the left of z equals negative 0.87 is 0.19, come on, 1922. But that's only the shaded region that I drew up here in red. So that's only this one. If I want the combined area, I need to now double this number. So if I double that number, we do 0.1922 times 2, I get 0.3844. So the p-value is 0.3844. So let me delete my table over here so it stops snapping back to it. So the p-value is now the combined area of both of those tails, and we can now decide if our result is weird. And is our result weird? No. Our result is not weird. And it's not weird because if I compare the two z-scores doing the critical value method, it's not weird because, let me put the word because in here, because our z-score of 0.87 is less extreme than the cutoff that we were going to consider weird, which was the z sub alpha over 2, the positive one on the right side was positive 1.645, which is the one it would make sense to compare this positive z-score to. And if we're doing the p-value method, instead of comparing two z-scores, I will compare the two areas. And in this case, it's because our p-value, which is 0.3844, is greater than the significance level, which was 0.1. We said we'd consider something weird if it had less than a 10% chance of happening. It turns out that ours has like a 38% chance of happening. We had a 38% chance of getting results as or more extreme than the ones that we got. So basically getting the discrepancy of our numbers here, the 0.495 and the 0.464, seeing that big of a difference of about 0.03 in those two proportions, that'll happen almost 40% of the time. So that's not a very unlikely thing to occur. So in plain English, well, we'll do this. So because it's not weird, so we are not going to reject the null hypothesis. And just checking what the null hypothesis said, the null hypothesis said that it thought the two proportions were the same, and we did not find strong enough evidence to reject that notion. So what we're saying is there's not enough evidence to suggest that these two populations use Instagram at different rates. So that's how I will phrase it. There is insufficient evidence to suggest that let me write it this way, that the proportion of high school students using Instagram differs from the proportion of college students using Instagram. So that's what we found. We did not have strong enough evidence. We saw a little bit of evidence that they used it at different rates, but it wasn't strong enough. It totally could have just happened by chance with the size of the samples that we happened to look at. So that is our conclusion. To do this problem on the calculator, we are going to hit the Stat button, go to our list of all the possible tests, and we're looking for, hopefully you can kind of anticipate what the correct one is here. We're looking for something where we use two proportions. There's two different proportions that we're computing. We're using z-scores and we're doing a hypothesis test. So this is a 2-prop z test. So 2-prop z test. And if I select 2-prop z test on my calculator, that is option 6. It may be different on yours. It'll ask for the following. It'll ask for x1, n1, x2, n2, and then it'll ask for the form of the alternate hypothesis. So it says P1. In our case, we know that's going to be not equal to P2. And we just need to go in and use the values that we used in our table up here. So just use all of these values from the table. So x1 is 213, n1 is 430, and so on. So this was 213 out of 430. The other one was 167 out of 360. Once we've got all of those in place, let me type mine in real quickly. Make sure I get my form of my alternate hypothesis correct and hit calculate. It spits out a couple of things for me. So it spits out the z-score, and in this case the z-score is 0.8814 ... It's a little bit different than the 0.87 that I found. I got this 0.87 because I used rounded versions of all of these numbers. That number is rounded, that number is rounded, that number is rounded. I used rounded versions in our formula for the test statistic, whereas the calculator used all the decimals. So it got a more accurate answer. It's still close, right? We got 0.87, they got 0.88, but theirs is more accurate because they didn't round any of those decimals. And similarly, for the p-value, they find their p-value is 0.3781-ish, ... Also slightly different than the value that we found up here of 0.3844, but again, it's because they didn't round. Their values are a little bit more carefully kept than ours. And then it goes through and it gives us all the other values that we might have needed along the way. If we wanted to write them down, it gives us p1 hat and p2 hat and p hat in general. And all of those numbers were the values we used. This is the 0.495-ish number, but it gives us more accurate, so 3, 4, ... P2 is 0.4, so 0.463888 repeating, it looks like. And the last one, 0.48101 ... So it used these versions in computing these two numbers. It used all the decimals, and that's why these numbers are slightly different than our numbers that we got up here because we rounded. So again, you can use this. It will give us these two pieces, which are basically the results of step 3 and step 4. So the calculator always gives us those two steps when we do one of these hypothesis tests. It gives us the value from step 3, and then it gives us the p-value from step 4. We still need to have the other parts done all by ourselves. So I will get another video done here for the last section, and then hopefully going forward you can practice a bunch of these, and I will try to highlight again what all the similarities are between all of these, and then highlight all of the distinctions and talk a little bit maybe in some sort of review video about how we can determine which approach to take. They're so similar. We've got 6 different types of hypothesis tests at the end of all of this. How do you know which one to use on any given problem? So we'll take a look at that in an upcoming video.